NanoHub U, online instruction.
Hey everyone, this lecture 215. In the last lecture, we just started talking about how to use Camphor. And of course, we said you can download it for free from camphor.sourceforge.net. And you can also download Python for free and install it in Python if you don't already have it. So continuing on the basic discussion we had earlier, we already showed how you can use it to calculate a 1D waveguide performance. Now we're going to actually look at what we'll call a 2D waveguide, where basically it's a waveguide with a finite length. Okay, and so this formulation here for our waveguide in 1D is actually almost identical as what we had earlier. But then we're actually going to also insist that we have like a spatial region on either side, okay, that has air. It has a total thickness of 4.5, okay? And this is essentially going to be semi-infinite on this side and then on the far right side, okay? And then we're actually going to allow the length of this gallium arsenide slab to vary in this direction, okay? So you can see this length here from one end of the gallium arsenide to the other is just defined as L. And then we allow L to go over a whole range from very small value to slightly larger value of 0.1. So it's still very short, of course, with this just a proof of concept. And then we can actually like stack these three layers, the air region, and then the gallium arsenide slab, and then the air again. And then we can perform the calculation, and then we can extract this so-called R12 parameter, which corresponds to the reflection starting from 1 and then reflecting back from the 2 region, if you will. And then, of course, there's a reciprocal term, R21. And so for a lot of problems, of course, these should match. And so then here's the results for the 2D waveguide that we calculated. Not surprisingly, if L is 0, then there's no reflection, right? Because there's nothing physically there really to reflect it. But as L gets larger, of course, the reflection starts to go up. And you can see that it doesn't go up just in a straight line forever. It does start to roll over because we're physically limited to a certain amount of reflection. In this particular case, it's rolling over around 35%, which very roughly corresponds to the Fresnel reflection of an air gallium arsenide interface. So it kind of seems logical. Now, we're not necessarily actually limited just to Cartesian geometries. Another possibility is to look at cylindrical stacks of materials. And so in this case, it's actually very analogous to what we just did, except that instead of having essentially a 1D layer or 1D stack that was here, we actually create a circularly symmetric stack. So while it looks almost the same from the side, you can see from the top that actually looks like a round piece of gallium arsenide. So you can kind of think of it as like a very high index fiber optic waveguide that's cut off into a very short stub, right? So it's a very short and squat cylinder that we're calculating here. And so you can see basically the way that we set this up is, first of all, we have to have these circular PML boundary conditions, which stands for perfectly matched layers. And so then this ensures that if the fields get too far away in the radial direction, then they get absorbed. And then we have to set up like an air circle, of course, to go above and below the gallium arsenide. And we have to set what's called the circular order, which is basically the symmetry of the input mode. And so in this kind of problem, we can probably assume that we have m equals 0 or m equals 1. M equals 1 would correspond usually to a plane wave, so that's also a common choice. But here we chose m equals 0. So it's like a circularly symmetric source. And then we can actually calculate, based on this structure, which is a stack of like an air circle and then gallium arsenide surrounded by air circle and then another air circle. So adding these three things together, calculate it, and then print out the reflection. And so then we actually get something like this. And so probably not surprisingly, again, if the radius of this cylinder is very small, then it doesn't really do much. But as the radius increases, then you can see that it has like a lot of peaks and valleys. And so this probably corresponds to like certain resonant modes that create like a stronger quality factor mismatch and thus stronger reflection. In the next lecture, we'll go through like another example of how to use camphor.